All right, so in this presentation, I will go over how to use the Weka program to analyze a data set. So basically in this example, this is Weka. Weka 3.8 is the program. It's already been installed. This can be downloaded from the Weka website. There are versions for Mac, for Linux, and for Windows, and it's pretty straightforward to install. The other thing we have is just a simple data set. So Fisher's Iris data set is usually one of the easiest data sets to understand. And so since this is, an introduction to, one of the tools, I'm going to use the Iris data set. Now, I actually really like Weka, even though you might want to use TensorFlow or you might want to use, PyTorch or sklearn whenever you're doing your machine learning. I do like Weka, and I think Weka has some advantages. It's not necessarily for big data, but it's a program that helps you to really quickly to get a snapshot of your data. All right, so that's one of the reasons why I like it. Makes using machine learning very straightforward, and so I will always try to view my data first with Weka before I do anything else. So what I recommend is if you're doing a big data problem and you have a million records or however many records you have, you can always just take a subset of that data set. And I have found that whenever you have a data set, a matrix that's something like 100,000 rows by 10,000 columns, that's usually small enough that it can be supported by an 8 RAM computer, a standard Windows computer, your laptop basically. And so really quickly, even though you're not looking at the entire data set, if the data that you have is starting to represent a sample, the distribution of the population, then it starts to give you an idea of what your data will look like. So anyway, so here is the two files that we're going to use for this example. Let me open Iris dataset first. So this is an Excel spreadsheet. And so usually when we load it into Weka, we're going to think of it as a text file. And so we're going to load it that way. But, because it's a CSV file, Windows opens it as a Excel spreadsheet. So the things to understand about this data set, which are, very important, and usually whenever you're doing machine learning, all your data will look like this. So in this case, the rows represent the samples. So that is to say, Iris is a data set that deals with plants, but every plant here is a row. And the people that analyzed the plants basically looked at 4 features. That is to say, 4 elements of that sample. So the sepal length, the sepal width, the petal length, and the petal width. All right, and apparently those 4 markers allow you to distinguish between different types of plants. So in this case, the types of plants are setosa, versicolor, and virginica. So this is a 3-class problem. Now, if you notice, these are words, and usually when you use something like sklearn or TensorFlow, you cannot use these as labels. Instead, you have to encode this into like 0, 1, and 2 numbers. But Weka is so easy to use, actually, that this is permitted in Weka. So we can actually just give it these words, and it'll basically convert it by itself. Now, as you can see then, this matrix has 5 columns, so A through E. The last column is the class, and you can see that's actually labeled here. And then the first 4 columns represent the features. So you can say this is F1, F2, F3, F4, or you can say X1, X2, X3, X4. If you notice, the values in the columns or the features are just numerical values that represent, as the titles indicate, the width and the of the sepal and of the petals, the length and width. All right, so other programs also, whenever you're loading your data, they will require you to remove the first row, the headings basically, or the titles of the columns But Weka does not require you to do that. So you can actually use this file as is, and Weka will basically know, okay, this is the headings. I'm not going to use that for machine learning purposes. I'm going to know how to encode the classes as well. But later on, as we will see in other videos, when we are using sklearn or TensorFlow, we will use some libraries to remove this first line, the headings, and we're basically just going to be using this. So really the data is this is x all the way down, and then our y vector is going to be this later on. All right, so anyway, so that's, I wanted to say a little bit about the data set. Okay, so now in our case, another useful use of Weka is that here we know we have 151 rows or whatever, 150 samples, but usually in other approaches or in other problems, we won't necessarily know the number of rows or the number of columns. So Weka is really good for just that, just to get a few statistics about your data set. All right, so let's go ahead and then I'm going to close this file. All right, and now I'm going to go ahead and open Weka. So this is the Weka program. And I'll just go through some of the functions of Weka. So as you can see here, the first thing it says is that Weka has a package manager that you can use to install many learning schemes and tools. So what this basically says is that whenever you install Weka initially, it only has a default set of libraries that are implemented, but not all of them are implemented. However, it does allow you then to, by using the tools here, right, package manager, it gives you the ability that you can click on this and start downloading more libraries. Right? So let's say, for instance, this is just an example that you wanted to use support vector machines, which is one of the advanced machine learning algorithms. Since that's not installed, you would go to package manager, select support vector machines, download it, and now after that you may need to restart Weka, but you would be able to run that algorithm. Okay? So that's kind of the idea with the Weka program. It's pretty easy and straightforward. So now let's go ahead. We're going to go through. So whenever you start it, let me go through the menu first. I should, I guess, give credit to the creators of Weka. So this is created at the University of Waikato in New Zealand. This has been around for a long time. The name stands for Waikato Environment for Knowledge Analysis. It's a tool that I really like, actually, and it's been around for a long time. So anyway, so here we have the main menu. So Weka is really a set of Java libraries. That's really what it is. So you can think of Weka behind the scenes as just a whole bunch of Java classes or libraries, code basically, that's in the background. So that basically tells you that if you write a Java program, you could also call the Weka libraries from your Java program and then build some application like that. Right? So that's a possibility. But in our approach, we really, as data scientists, we really don't necessarily want to build applications with Weka. We just want to use it for really quickly visualizing our program. So there's various approaches here, like a command line way of doing things. I usually focus just on these two, the Explorer and the Experimenter. All right, so and I'll talk about them in various videos. Today I just want to do a really quick example of the Explorer, and then maybe talk a little bit about the Experimenter. Experimenter is actually pretty good, I should say, and it's useful for people. So whenever you think of machine learning, you can look at machine learning from a practitioner, like a machine learning practitioner, or you can look at machine learning from a statistician point of view. So whenever we think of statistics, for instance, whenever we say that something is significant or we have a result that we think is important, statisticians would ask us, well, you say it's from your experimental results that this is better than, A is better than B, but is it really statistically, is that difference really statistically significant? All right, so doing the famous t-test. All right, so whenever you think of doing a t-test, think of the experimenter. All right, so whenever you want to maybe compare with, given one data set, you want to compare 3 algorithms, and you want to look at their performance metrics and be able to say, yes, method A is better than methods B and C. Well, the advantage of using the experimenter is the experimenter adds the additional t-test to tell you, oh yes, I think it's better and I think it's statistically significant. All right, so that's one of the important issues here. So, oops, sorry, I didn't mean to do that yet. Okay, and so later on I will explain a little bit more about the theory behind a t-test and statistical significance of machine learning using either experimenter or just regular Python code. But just for now, be aware that that is the reason why, or one of the advantages of using the experimenter. However, initially though, you don't usually want to do the t-test. You just want to kind of get a quick glance of your data. And so for that, you can just click on Explorer, all right, and then you get this screen here. Now, so I'll talk a little bit about the layout. So, all right, so if you want to get to the Explorer, you can click on the Explorer button, and you get this window. Okay, so with this window now, this is where you can view the Explorer information. So let me just talk a little bit about some of the things that are available here. So open file is really, as you might imagine, the button for loading the file. All right, so Weka allows several formats. So it has its own built-in format called a .arf format. It also has other formats like CSV, and it also has libsvm and other things like that. So in our case, our file is a CSV file, right? So this is a CSV file that we're using, and so it will be able to load CSV. All right, additionally, we have this filter. Now, filter is a tool that is very useful. All right, there's various things that you can do here to convert the data. So for instance, let's say that your classes, the values in your class are like numbers, right? 0, 1, 2. So it might be that, that can be classified, that, that type of, that variable type, right, can be either numerical or it can be nominal. So whenever that value, that column, the values there are numeric, then usually Weka is going to interpret the problem as being, oh, this is, I'm supposed to predict numbers here, real valued numbers. So this is probably a linear regression, right? Whereas sometimes the values in that column could be, instead of the 0, 1, and 2 being numeric values that you want to predict, they're more like categorical values. So in that case, they need to be called nominal. Right? If they are nominal, then Weka will say, oh, this is not a linear regression. This is a supervised learning problem. It's supposed to predict classes, so I'm going to interpret it that way. All right, so that's what filter is. So if I click on choose and then I click on filters, you will see that I have various filters like supervised, unsupervised, and then if I click on attribute, you can see I have all of these. All right, so for instance, if I want to change all the values in a class to be from nominal to binary, then I would use this filter. All right, or if I go to instance here, right, I have, oops, sorry. If I go here to instance, then I have, filters for resampling, and various other things. If I go to unsupervised, I click on attribute, and now you can see I have even more filters. So for instance, the one that I was talking about, which is one that I usually use, is this filter, numeric to nominal. Right? So numeric to nominal allows you to take, as I said, the type of a column and changes it from being numeric to nominal. All right. And so there's a lot of filters here, and really exploring these filters is probably the best approach. For now, though, I'm just really going over the basics. So there's other other filters here as well. Randomize, you can randomize the values in a column, and so on. Resampling the size, etc. All right, so let's go back then to, so let me close this, or actually let me just finish discussing these. So one important aspect of Weka is that it has all these little screens that provide information about the data. So once we load the data, you'll see that it's going to list the attributes here. It's going to give you some statistics about the data set here. If we want to view the actual data, this will become highlighted and we'll be able to see it. And here in these two windows, we'll get some basically statistics of the features. So let's go ahead and do that. So I'm going to repeat the process. I'm going to close it, click on Explorer. Now I'm going to go to Open File, and I'm going to navigate to the desktop here. Okay, now if you notice, the file is on the desktop, but it's not showing because it's currently, the file type is .arf, so it's looking for an ARF type file. So what I'm going to do is I'm going to select CSV. Well, let's just do all files then. So here at the top, all files. All right, here we go. Now we have a few of the files that we need. All right, and here is iris.csv. So I'm going to click on it, select it, and now I'm going to say open. All right, and there it is. So now if we make this a little bit bigger, you can see this is the iris data set. It's saying that there's 5 attributes. There's the 4 features plus the column. So that's why there's 5. So 1, 2, 3, 4, 5. All right, it tells you the number of samples, which is 150, the number of instances there, here, it's 150. If we click on any one of the samples, like if I click on Sapal width and I go to this window here, now it's telling me this is, the type is numeric, this is the Sapal width, and it's giving you basically the minimum and the maximum of all the values in that column plus the mean and the standard deviation. And I can also view it based on the different classes, right? Kind of the distribution of the classes. Now if I look at the class, you can see there's 3 classes. There's blue, red, and light blue, right? There's 50 each of the classes. So this is 50 samples of Setosa, 50 of versicolor, and 50 of virginica for a total of 150 samples. You can see here, I can click on Setosa and it tells me that there's a count of 50 basically. And that's it. All right, so in this example, the data is pretty straightforward because it's already nominal. And this is very important, right? So if we look at the data type of the columns, this one is numeric as it should be. 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 And this one is nominal, which is correct, that because it's a classification problem. However, it happened automatically because the labels were like words, right? Virginica, Setosa. But if these had been 0, 1, and 2, what usually happens is that the class will be loaded into Weka as a numeric category because it looks at it as a number. So when that happens, what you have to do is you have to go to the filter, right? You have to click on the filter. You go to unsupervised, attribute. You select numeric to nominal. You click on that. Then you need to click on this white space. This is something that's a little not so intuitive with Weka, is that you don't always realize that to modify things, you click it, it opens this window here, and then now you have to tell it which attribute you want to modify or which attribute you want to apply the filter to. So in this case, we only want to apply this filter to class, right? So we would say, 5, for instance, right? So we select that index. Right, you can leave everything else as default. You click OK. And then once you're ready, you would click on the button Apply. I'm not going to click on it because it's already a nominal. But if it wasn't, once you click Apply, then the class data type here would change from numeric to nominal. Now this is important because if this said numeric here, whenever I go, so if you notice, whenever you want to navigate to do all the different machine learning steps in the pipeline in Weka, you navigate through these tabs, right? So for instance, pre-process just means getting the data, looking at it. Once you want to do the actual classification, you click on classify, and then you select algorithms here. Now, naive Bayes, for instance, is a standard classifier, right? I think we discussed it in one of our previous lectures. Now, however, if this value here was numeric, then whenever you went into classify and you look for the naive Bayes algorithm, what would happen is you would see that they're not highlighted, which is basically Weka's way of saying I can't apply naive Bayes to a numeric or linear regression type problem. Obviously, we're not having this issue because when we go to pre-process, our class data type is nominal already. But anyway, that's something important to know about. The edit button here, whenever you click on it, it's really handy. It allows you to look at the data set, as if you were looking at the Excel file or the text file. So this is useful. All right, and then once we have this, everything is pretty much ready. We're now ready to do some machine learning. All right, so what are a few things that you have to do in machine learning? First of all, you have to select an algorithm. So I'll go through the algorithms that are available here. So these are the classifiers. They're kind of grouped into like Bayes, trees, Lacy algorithms, and functions, and so on. All right, so I won't talk about all of those. I haven't used all of these. Usually I have like a few 6 or 7 algorithms that I like to use. So let's start with naive Bayes. So I think, as you can see, there's several versions of it. Usually I'll select this naive Bayes. As I said in a previous video, naive Bayes is a good algorithm. It's kind of a baseline algorithm. It's pretty fast to run. The accuracy of it is not great, but sometimes, you really just need a simple algorithm. You don't have to use such a very advanced algorithm, for instance. All right, so anyway, so this is naive Bayes. Okay, so that's one of the algorithms. Then we have, usually what I would do is I would go to functions, and here I have 2 algorithms that are kind of useful. Multi-layer perceptron, this is a neural network actually. Is it practical to use neural networks in Weka? Not really. Usually, for my, whenever I've taught this class, my students always have this, they're surprised that they did all the algorithms. Naive Bayes took, an hour, they say, on our data set, and then when they tried multi-layer perceptron, they just give me a smile and said, well, I left it overnight and it's still running, or something like that. So the algorithm isn't always the fastest. So if you have a small data set, you can try it. But usually, if you want a neural network, that's why we're going to learn TensorFlow. So you're going to want to use something like that. But these are some of them. Multi-layer perceptron, simple logistic regression. You can definitely try that one. That's one that I sometimes try. The Lacy algorithms, IBK, this is the KNN. So we did a discussion on, there's another video in our series where we talked about the KNN algorithm, right? And that's basically this one, IBK. All right, so just, you can set the parameter of what the value of K should be, but this is, the K nearest neighbor algorithm. Then decision trees. So J48 is the standard decision tree. And then random forest is basically usually kind of like decision trees, but always does better. So think of decision trees maybe as one tree, and then random forest as several decision trees working together. All right, and so these are the algorithms. There's usually more, and some are not available by default. So for instance, like support vector machines. So I think if you go to functions, I think this is where once you've installed support vector machines, it would appear. Now another interesting thing I want to mention is, if you notice here, linear regression is not highlighted. And that is because, as I said initially, our class is a nominal class. So it's not a numeric class. So that means, that tells Weka that this is a classification problem and not a regression problem. If that class had been numeric, then the classifiers would not be highlighted, and instead linear regression would be. Right? But right now we're doing classification. Now the next step, let's say I'm gonna stay with naive Bayes, so I'm gonna click on naive Bayes. Now the next step in the pipeline, whenever you're doing analysis, is you want to select your data. So currently we have our data set like this, and we have all of it, all 150 samples. So there's two ways that practitioners do machine learning, right? So they might have one training set, one file that's the training set, and one file that's the testing set. You might be asking yourself, but how do you do it here where you only have one file? So that's what this is for, test options. So basically, if we had a training set and a test set, two separate ones, we'll do another video where we have that, a train set and a test set, then we would use these two options here. So what I would do is I would select use training. I would load this file. This would be the training set file. And then I would run it. I would run the algorithm, right? And then it would create a model based on that training set, which would appear here. You would have a new entry here that would say, oh, the model has been created. Then once that model has been created, then what I would do is I would click on supply test set, click on this button, select my test file, and then I would apply this model to it. All right, so as I said, I don't currently have two files, so I will create another video just in this series just for that approach. But that's usually, so you use these two options whenever you have two separate files. In our case, though, we only have one, and this is very common usually in machine learning. You just got all your data, you're pretty excited, you converted everything, and now you just want to quickly take a look at it, right? So as we know from the discussions in the lectures, we know that whenever we do machine learning, we really want to have at least two data sets. Usually you have training, validation, and testing, but it's enough to have just training and testing. And how that works basically is that you take the train set, you build a model just looking at the data in the train set. You've never actually looked at the test set. Once the model is created, you apply it to the test set and you see how the model does. So obviously both of those are annotated, they have labels. So for one, the labels were used to learn. For the next one, the labels are used to determine how well the model is performing, because it's going to take the sample, based on the sample, predict the class, and then it's going to compare that class to the actual class. So that's what this is for. So usually these two options allow you to split this data set. So let's say that we have 150 samples here. So I'm going to do, let's say, percentage split, right? So I'm going to select 70%, right? And now what that means is I'm going to grab 70% of the 150 samples, and this actually selects them randomly. So it's not just going to grab like the first 70% for training. It actually will select them randomly, and will perform the analysis that way. All right, so once I've selected 70%, I can go ahead and select the class. So in this case, it's pretty straightforward. It's obviously not these four. These are the features. The class is this one. So you want to tell it what the target is. And once I've done that, I can just go ahead and hit start. And there you go. As you can see, naive Bayes is pretty fast. And now we get this. This is the output, the performance metric. So of any machine learning algorithm, you usually look at the confusion matrix, you look at the precision, you look at the recall, and you look at the F measure. So in one of the lectures, we discuss what all of these are and their definitions. So I'm not going to discuss that here. Instead, I'm just going to really talk a little bit about how to interpret what we are looking at in this screen. So usually what you'll see is that you have an overall accuracy, all right? That's the overall accuracy of your problem. That's like 95%. But this also breaks this down by category, right? So you have like, these are the classes, Setosa, Versicolor, Virginica, and overall. So that's why we have 4 rows, because it's telling you how well the algorithm did for each of the classes. How well does it predict? So we can see here that we have a precision of 1% or 100% basically for Setosa virginica, but it's only 89% for versicolor. So that tells you that it's getting the precision right on versicolor is a little bit harder. Recall, here we can see the results. We can see that overall the precision was 96. That is pretty good for machine learning. The recall here is pretty good, 95. And then F measure, as we discussed in another lecture, another video, is a harmonic combination of precision and recall. So usually that's why practitioners, since it captures a little bit of both, they look at F measure. And you can see the F measure is pretty good, 100%, 94%, 92%, and overall it is 95%. Now here we also have the confusion matrix, and the confusion matrix is very useful because it tells you how something was misclassified. So for instance, if the diagonal is the only part of the matrix here that contains numbers and everything else is zeros, that means that basically we had a perfect classification. Now, iris is a very easy data set to classify, and so you can see that most of these are zeros. We actually just have one, a 2 basically outside of the diagonal. Right? So that this basically can be interpreted as a saying that out of all the values that should have been C or iris virginica, 13 were correctly classified that way, but 2 were misclassified as versicolor. That's what that means. Whereas with the Setosa here, we can see that out of 14 that we had in the test set, 14 were correctly classified as Setosa, and there were no misclassifications. So that's basically the interpretation of this data set. Okay? So what about this one, cross-validation? So cross-validation is a little bit different. Cross-validation just basically says that instead of splitting in 70%, 30%, we're going to split the data into 10 bins of equal size. So for our purposes, it would be 15, right? So 15 times 10 is 150. And so we would have 10 bins of 15 each, all right? And now it's going to repeat the same process 10 times, and it's going to give us the result based out of 10. So for instance, what it does is it divides the data into 10 bins. In the first iteration, it grabs the first bin for testing, and it uses the other 9 bins for training. Then the next iteration, now it's going to take the second bin, leave that out as a testing set, and use bins 1 and then 2 through 10 as the training data. And now it repeats everything, calculates the results, does the same with the third iteration. It grabs the third bin, it uses that for training, it leaves out all the other bins, it leaves that one out for testing, and it takes out all the other bins, and it uses those for training, and so on. So you can see basically the approach. So 10 in that sense, 10 cross-validation should be better. All right, so let's go ahead and try that. So now I'm going to use, and you can see now, the results now, you can see the confusion matrix changed a little bit, right? Because it's taking kind of a look at everything that's available in the data set. You can look, but you can once again look at the results, F measure, confusion matrix, etc. All right, so that's basically the difference between percentage split and cross-validation. So now that we've looked at naive Bayes, let's kind of just stick with 70% split here, and so that we can compare other methods. Because ultimately you want to be able to compare apples to apples, so you kind of want to select something that is a consistent number. So we're going to use percentage split of 70, and now let's select another classifier. So I'm going to use the logistic, or let's use multi-layer perceptron. This is small enough that this should be fast enough. So now I'm going to hit start, and there you go. You can see now if I want to compare naive Bayes to multi-layer perceptron, well, I look at naive Bayes. Just one quick glance at it, the F measure was 95 overall. With multi-layer perceptron, it went up to 97. Now, is 97 statistically better than 95? I can't really say that, right? I don't know. I can see based on these results that it is, but I don't know that it is statistically significant. So that's where a t-test comes in, and that's where we would use experimenter. So I will discuss that in another video, but that, I kind of wanted to illustrate that. Let's pick another algorithm. As you can see also, whenever I pick an algorithm, I don't actually have to change too many of the parameters. I'm really just using the default values. So I'm going to use IBK, which is KNN, all right, and I'm going to run it again. And you can see now I have the new model, IBK, and the accuracy is about 95. So far, multi-layer, if we're just looking at this one metric, F measure overall seems to be the best one of all of these. Now, are we always going to get really high values like this? No. In the future, you will see that actually, with our data sets, with more real data sets, the accuracies or the F measures, etc., are actually quite low. The confusion matrix is all over the place. And so we will see that in the future. Let's do one more. Or a couple more. So let's do J48, which is the decision trees. This is another one that I like to use. I'm going to hit on start, and you can see the results there. You can see that F measure is 0.95. So it seems to be there's kind of a trend going on, right? So at this point, and this is why I always like to use Weka, because it gives you this. Now really quickly, I kind of now have a picture. Everything seems to be hovering about 95, 95, 95. Multi-layer apparently did 97. Does that mean that a deep neural network would get 100? I don't know. But, it kind of starts to paint a picture of your data set. Obviously, when you have a data that's newer, that's more noisier, etc., this becomes useful, right? It starts to paint a picture or show a pattern. Let's do one more. Let's do random forest. We look at decision trees as 95. Now I do random forest, and it's still 95. So there wasn't any kind of improvement. But anyway, that's quickly how you can use Weka to prototype your data. These are some of the nice algorithms that I like using. One last thing that I will mention, that another feature that I really like to use in Weka, more so really than in any other data set, is its ability to tell me which features contribute the most to solving my problem. So Weka has a ranking tool that allows you to take, basically it's like you're saying, okay, so what are the features that are most important to classify things correctly? And so this is the example. So for instance, I did in another video where we talked about intrusion detection systems, right? And we have 3 features. Protocol, which is 6 for TCP, and then we have source port and destination port. So right there we have 3 features. It's an IDS system, so we want to basically classify something as either being an intrusion or not an intrusion. So what the ranker would do is, well, if all the packets that we're looking at are TCP packets, then it means that that value of protocol is always 6 for every single one. So what Weka would do is it would rank source port, destination port, and protocol, and it would rank them by significance. So it would say here, protocol is the same for all, because they're all TCP packets. So actually, protocol has no contribution to this problem. So it would rank it last, and it would probably give it a value of 0. All right, and by giving it a value of 0, basically you can really get rid of that feature. You don't need it anymore. All right, so let's try that with Iris. So to do that, I'm going to go to select attributes. All right, and usually you can search the methods. You can select a method. So in this case, I'm going to say ranker. I want to basically rank my features. And Weka then very conveniently will suggest the method that you're going to use. So here it says you must use an evaluator that evaluates single attributes, such as information gain. So usually I'll use either the chi-square method or information gain. In this case, Weka suggests information gain, so I'm just going to go with that one. And that's really what I would say is that there's some math, some statistical math involved in this process. And that's what that is doing. It's basically saying which of the methods that are available would you like to do. But at the end of the day, all I care about is the ranker. Now I can use either the full train set as is or cross-validation. What I suggest to practitioners is really just use both. Okay? Make sure that the class is selected correctly. So in this case is class. All right, and now I'm going to hit start, and there we go. Because this is such a small data set, it doesn't take very long to provide the list. So here are the results. As you can see, according to this, it's telling us that the petal length, that one of the 4 features, has the highest contribution. It has a value of 1.4. Then the next important one is petal width, has a pretty significant contribution of 1.378. Of the 4 features, apparently sepal width is the least important, with a contribution of 0.376. That is its value. And so this is very useful, and we will use this more in a few other data sets just to kind of get a better understanding of the ranking of the features. But this is a useful tool. So in my analogy of intrusion detection systems, we would see basically protocol here with a 0, no contribution, and then maybe destination port would be 1, and followed by source port, and so on. So especially for people that, cybersecurity experts, right? Cybersecurity experts, where you have a lot of, elements that you need to analyze. Maybe it's a malware, dynamic analysis of malware problem, and you want to know, should I focus on registry edits, for what the virus is doing, or should I focus on DLL calls, or should I focus on writing to files, making internet connections, and what have you, right? So, if you have an annotated data set of malware and goodware, you could load it into Weka, run the ranker, and then maybe it'll give you here a list of what it thinks are the most important features. And then maybe it says, DLLs are the most important, it seems, at least according to this data set, to detect malware. And so then, therefore, the cybersecurity professional could maybe focus on DLLs, right? Focus on that particular, what are the DLLs that are associated with these viruses, etc. So anyway, so that, it's a use for machine learning, machine learning can give you that kind of information. So the interpretation of this, again, is to determine what is the contribution of the features, which ones are better at solving this problem. All right, so this kind of concludes this discussion of how to use Weka with a simple iris dataset. It's our first introduction. Later on, I will come back with other data sets, and we will also look at the experimenter and when we discuss t-tests and statistical significance.